So this was on our 2023 exam. Uh, didn't have to didn't have students calculate frequency and energy of each of these lines, but depending on the version, each student got one of these lines. In the previous video, I went about this in a really roundabout way, so I'm just redoing this in a much more straightforward fashion. So let's do this first one here with the wavelength given us in nanometers, 410 nanometers. We can get the frequency simply by using this equation where the speed of light is equal to wavelength times frequency. We're going to rearrange that and get frequency is equal to speed of light over wavelength, and now we can just plug in our values. The speed of light is given to us on your reference sheet as 2.998 times 10 to the 8 meters per second, and the wavelength here is given to us in nanometers, but we can convert that into meters to cancel out the meters given in the speed of light. With this conversion factor, 1 nanometer is equal to 10 to the negative 9 meters, which is also on your reference sheet. All right, so 1 nanometer is equal to 10 to the negative 9 meters. Then 410 nanometers is going to equal 410 times 10 to the negative 9 meters. Now we can see the meters cancel out, and we're left with units of wavelengths per second, or hertz. Now we can just punch these numbers in our calculator. 2.998 times 10 to the 8 divided by 410 times 10 to the negative 9. All right, and we'll round that to, well, these are all on the same measuring device, and you know they have precision to the ones. So just because of that, if it was just 410, it would have two significant figures, but because these are all in the same, using the same measuring device, we know it has precision to the one. So we'll give you three significant figures. If you got this on a test, we would specify 3 sig figs if we wanted it. So let's get 7.31 times 10 to the 14. You can say hertz, or you can say wavelengths per second, or cycles per second, as somebody pointed out, or per second. And that's the frequency of that purple line with a wavelength of 410 nanometers. Now we can take this frequency, which we just solved for, and plug that into our next equation, which is energy is equal to Planck's constant times frequency. And we're just going to plug in our numbers here. Planck's constant is given to us on our reference sheet, 6.626 times 10 to the negative 34 joules times seconds. And we're going to multiply that by the frequency we just got. Okay, and I'm actually going to change that from hertz back into per second. All right, so 7.31 times 10 to the 14 per second. And we'll see that the seconds cancel out, and we're left with joules, which is a unit of energy, the SI unit of energy. All right, so I'm going to use the number in our calculator, not this rounded one, and let's see what we get. So that number is already there. I'm just going to multiply that by 6.626 times 10 to the negative 34, and we'll get 3 sig figs again and get 4.85 times 10 to the negative 19 joules. So you would do that for each of the other lines, and maybe I'll just show my work. Yeah, all right, I'll do it. So the next one here, and you can just skip ahead here and get to the answer. 434. Speed of light is equal to wavelength times frequency. Therefore, frequency is equal to the speed of light over wavelength. 2.998 times 10 to the 8 meters per second, wavelength for that blue line is 434 nanometers, which is the same thing as 434 times 10 to the negative 9 meters. Meters cancels out. That's going to give us, let's clear this out, 2.998 times 10 to the 8 divided by 434 times 10 to the negative 9. Three significant figures, 6.91 times 10 to the 14. You know, I'm just going to go second set of negative 1. Switch it up a little bit. So there's our frequency for that blue line. Plug that into E equals Planck's constant times frequency. We're going to get 6.626 times 10 to the negative 34 joules seconds. Multiply that by that frequency we just solved for. Second set of negative 1, just writing it a little different way so you get some different views here. So that's going to cancel out with that. We're left with joules. That's going to give us units of energy. Punch, punch, punch. That number is already stored in there. I'm going to multiply that by Planck's constant, which is 6.626 times 10 to the negative 34. Three significant figures is going to give us 4.58. 4.58 times 10 to the negative 19 joules. All right, let's move on to the orange line. I'm sorry, green line. This is the atomic emission spectra for hydrogen. So 486, green line. 486. Let's write it this way. 486 nanometers is equal to 486 times 10 to the negative 9 meters. Cancel, cancel. All right, here we go. 2.998 times 10 to the 8 divided by 486 times 10 to the negative 9. That's going to give us frequency. 3 sig figs is going to give us 6.17 times 10 to the 14. We'll go with 1 over seconds this time. Just mixing it up. They all mean the same thing. Now let's punch that number into times Planck's constant to give us energy. It's Planck's constant times frequency. So that's going to be 6.626 times 10 to the negative 34 joules seconds. And we're going to multiply that by that number we just calculated is our frequency, 6.17 times 10 to the 14, 1 over seconds. Seconds cancels out. That number's still there. Multiply 6.626 times 10 to the negative 34 is going to give us 4.09. 4.09 times 10 to the negative 19 joules. Finally, a red line. Let's go to our red here. All right, we got 656 is the wavelength. Clear this out again. 2.998 times 10 to the 8, that's the speed of light, divided by the wavelength is 656 times 10 to the negative 9 meters, 4.57. Let's go back to hertz. Energy of that photon is Planck's constant times the frequency of that photon, and that's going to be Planck's constants given to you. And plug in the frequency which we just calculated. .03. All right, let's see if this makes sense. The red light is the lowest frequency, so it has the least, should have the least amount of energy, and the purple should have the most. So is that what we got? Yes, that's what we have. All right, so 3 is this is the lowest energy, and this one here is the highest energy. So all makes sense.